All right, and you guys probably want me to do, what is it? Go
present.
Present.
Since you ad hoc booked this room, we need to give it a name so you can type it in. It's like when you go to present, it will usually auto connect you to the meeting of your calendar.
All right.
If you do an in-room booking, you don't get that feature. So I think what you do is you click on the in-room booking, and then when you give a code, let's call
API.
it. Let's see if that's showing up.
All right, go present.
And I think you somewhere there you can enter a meeting code.
API, right?
Yeah.
Application window in the Zoom meeting, I assume? Or do I want to just
There's nothing on the
my entire
schedule.
screen, or just?
You could do it either way, both work. I always do my entire screen, but the other one should be fine too.
All right.
I don't know what we're going to talk about because it's still early.
Well, we can always do it short.
That's good.
There is nothing to say we have to take up the whole time.
Yeah, I'm sure nobody will complain if we tell them they can go.
I think there was one person who wanted to show up, however, and all right, so we have, no, that's the 14 meeting notes. Damn it, too many meetings.
Yeah, I don't see anything. It's empty.
That's the weirdest thing.
Zoom. There's the API Machinery agenda notes. There was something in the Slack, I thought.
Let's go look over there.
Yeah, tell me if there's anything in Slack. Hey, can you hear us?
Yes, I can hear you.
Awesome.
I can see you too.
That may not be as fun.
I don't know any of you by sight. I'm Mike Spreitzer.
Hey, Mike. I'm Walter, otherwise known as Chef Taco.
Hi. Hola.
And then we also have a few other folks in here.
This is Joe Betts. I work mostly on etcd. This is Howard. Work on client side, I guess.
Jenny, I'm right now just fixing bugs.
She's currently acting as our webhook, our validating webhook expert.
All right. Nice to meet you.
Awesome. So we can't actually come to any decisions today because we are missing both David Eads and Lava Lamp. But if you have any questions or anything you wanted to discuss?
Yes.
Actually, before you do that, I am suddenly realizing that I should record. Now I just need to work out where the record button is.
It says recording in the corner.
It does? Awesome. Never mind, we're good. Wanted to make sure it's being recorded.
Okay.
Hey, Chow. So we also have Chow joining us.
Hi, Joe.
Cool. Sorry. So before I rudely interrupted you, you were about to ask?
Oh, I was just going to say, I do have an open issue I'd like to discuss to the degree that we can with the people available.
Sure. Great.
I'll post a link in the chat there. So the background is I'm interested in using the Kubernetes API machinery to just build distributed systems in general. I think the idea of focusing on, as you guys say, level-based rather than edge-based management, and the idea of watches is a good way to build distributed systems in a way that's simple and reliable. And I'm trying to do that. And to support that, I'm studying the performance of that machinery. So I have constructed a simple test micro benchmark. I took the example aggregated API server which implements objects called flunders for some reason, and the example controller, and modified it to work with flunders. And all it does with flunders is basically log timing information. So I wanted to study the latency from the time that the client does an operation on a flunder to the time that all these controllers, which I call loggers because all they do is log timing, receive the information. And I wanted to study the latency and then the costs in terms of CPU, memory, and network along the way. And so I've been doing some experiments, and there's a pointer in that issue to a Google Docs site where I'm compiling results of those experiments. And I'm finding that in the normal configuration, where these loggers connect to the main API server, which in turn proxies their watches to the aggregated API server. And I'm starting with very simple configuration where there's just one of each, and each has its own etcd server. Basically, I'm using the sample API server config, which has a pod with an aggregated server and its own etcd server in it. And deploying with kubespray, which puts up one API server and one etcd server. Anyway, in that configuration, I find I can't use up all the CPU and network. Whereas, if instead I make the loggers connect directly to the aggregated API server, which is relatively simple by just hacking their client set object, that I can use up the CPU on the machine that is running the aggregated API server. So I think that there is some internal bottleneck in the proxying mechanism for watches that is, limiting it.
Yeah, I would imagine that's true. Quick question. So we've got the main API server is presumably doing, and I need to validate this, is doing a watch against the aggregated API server. The aggregated API server is then also doing a watch against its storage layer?
No. The main API server is simply proxying each watch. So the aggregated server sees a bunch of watches on Flunder objects.
Right. But that API server is, I don't remember the Flunder implementation well enough. Do we know if it is itself? So the default would be it's using etcd, etcd under the covers.
Yes, it is using etcd.
I'm sorry, what?
Yes, it is using etcd.
And then, so I would assume, but I would like to, we can validate whether it is then doing a watch against etcd.
Right. I would assume. Right. Again,
I would
my
assume
point
as
is,
well, but it's probably worth one of us validating.
I have done some with V turned up to 10, so I think we can see in pretty great detail what happens. I'm not sure with our shared logs from that, but I can do that if you like.
I think we just need someone to check. I'm just trying. Partly, I'm just going through the details, seeing if I can trigger any thoughts in my brain as to what might be going on.
Right. Well, I'll remind you that the two cases I'm comparing, in both cases, the aggregated API server is getting watch operations, so it's serving the watch operations presumably the same in both cases.
Yeah, I mean, the interesting thing is that unless I misremember how the API server implements watch, it is essentially just an open request which gets replied to when there is data available. So it's not exactly, I mean, it's all push-based rather than pull-based.
Yes. All right, the implementation of a watch, it's an HTTP request response. Over HTTP1, it is a response that goes on for a long time using the chunk transfer encoding.
Yeah, it seems like we'd be much better off with HTTP2, but...
Oh, well, yes, it does. Right, the Go code does use HTTP2 when you're using TLS, unless you take steps to disable it. So I explicitly qualified my remark. In HTTP1, it uses the chunk transfer encoding, but in this case, the actual traffic is using HTTP2, which doesn't use chunk. It doesn't have chunk, but it has this framing concept in HTTP2, and so it just sends a series of frames back whenever it has something to say.
Yeah, so the weird part to that is that if it's all push-based, it's sort of, I'm having a hard time thinking what could be going wrong between the central API server and the aggregated API server such that you're limiting, and the only thing I can think of is there's some sort of delay in how long it is before it, reestablishes that it wants more data. Daniel, so the claim here, I don't know if you're familiar with this.
Yeah, I've opened this document in a tab and have had zero time to start closing tabs as opposed to opening them.
Sure. So the claim here is that if you do a watch directly against the aggregated API server, you can consume as much resources as you need, and you can.
Oh, to be clear, this is not about one watch. This is about hundreds of watches.
Oh, sure, but the key being the difference is the direct, directly watching against the API server rather than going against the central the Kube API server, which then aggregates. And that somehow that the aggregating the watches is preventing the system from scaling well.
Refresh my memory, because I saw the document, but I don't recall. Is the problem in sending items through the watches that doesn't work, or is the problem opening up a new watch, starting a new watch?
I believe the problem is getting the throughput through the watches.
Yeah. The watch works. It's a matter of how well it scales, and apparently it scales well when not aggregated, but doesn't scale well when aggregated. So it's like it's not being driven quickly enough when aggregated.
It's like there's an I/O limit or something in the main interface.
Right. There's a throughput limit. So the failure symptom, when the proxy case hits the wall, what goes wrong is watches fall behind, and they terminate early. And when the informer or reflector says, pick up where you left off, the server says, oh, that's way long ago, I can't do that. And so it has to do a list again, which costs even more bandwidth. And so
that part makes sense to me, but
it's is it CPU bound or IO bound?
No, that's the trick. It's not CPU bound. It's not hitting the network capacity. I'll tell you, my primary suspicion is in the fact that this proxying is done over one TCP connection. The HTTP2 mechanism is doing multiplexing and demultiplexing over one stream, and that's logically a serial operation. So there's going to be a bottleneck, a multiplexing on the aggregated API server, all those responses back down into one TCP connection. And similarly, there's going to be a bottleneck demultiplexing them all into the various watch requests on the main API server side.
Actually, not a bad
That
suggestion.
sounds pretty plausible.
Yeah.
You should, let's see, to test that.
That should be pretty easy to test.
Why do you need to test it? Because you just look at the code and see.
Well, the problem is that, I mean, if he's right, and I think he probably is, that what we're really talking about is essentially it's a lock contention problem.
I wouldn't call it a lock contention problem. The lock is just an implementation detail. The real problem is that there's this logical necessity to multiplex a bunch of concurrent response streams into one TCP stream, right? And that inherently is a serialization thing. It doesn't matter whether you implement it with locks.
Well, yeah, but I mean, you have to lock to do the serialization. Anyway, I don't. If you don't mind, I'd like to not get too quibbly on that. The point is that there's a contention problem.
Exactly. There's this contention that's inherent in the fact that there's one serial stream.
And if we did something as simple as just put in a second one, we should, if he's right, we'd double the throughput.
Exactly.
Which would confirm
if you could get the main API server to actually talk to both.
It would be enough to prove this, or an interesting experiment would be, say, if we could still just one main server, one aggregated server, if we could just get two TLS connections between them.
Yeah, and you should be able to do that, but you'd have to recompile and probably disable.
I think you can be even sneakier.
No.
No. So this is what I'm trying. If you get two, it gets easy to test, right? The aggregated API server has both flunders and flinders. What you do is try having one aggregated API server with flunders and flinders. Then you attach two aggregated API servers and give each one of them flunders, give one of them flinders, same set of watches, split 50-50, and you should see a doubling of performance just by splitting across two aggregated API servers, because now you're dealing with
right.
connections.
Right.
Shouldn't require
Which shouldn't require it. It's a config change, not a code change.
Yeah, it's fishers. It's Flunders and fishers.
Oh, Fishers, sure.
Let's see. Yeah, I'd have to
That
make
would
the
be a very quick way of confirming this.
So we'd have to, well, we'd have to put the Flunders and the fishers in different servers, though, right? Otherwise, the main server is going to use one connection for both of them.
I thought it was which aggregated API server was a
Yeah,
config.
you can just configure the API service object to go to one or the other.
Well, but I thought the API service object is by the group and version. Maybe not even version, but it's by the group, right? Not the object type.
It is.
Let me just double check. I mean, I've got the running
It
system.
is by group version, and
So you might have to
so you might have to modify the group or the version or something.
on one of them.
I'm actually not sure how smart the Go HTTP client is. It might, if you use the same IP address and port for each, it may actually still multiplex.
Well, this is what I was thinking. If you, I mean, it's not a perfect solution, but if you actually just bring up two copies of the service, then each on a different IP port.
Right. You're right. It would be easy enough to bring up two servers, but that's now more of a difference. So it's not totally
It's not perfect, but what I mean, I think I liked the way Daniel put it better than the way I put it. If that doesn't double your throughput, then we're on the wrong path.
Yeah, I think
that
that's
doubles your throughput. Then we haven't proven it, but we've added some pretty strong weight to the theory.
Exactly.
Yeah.
We haven't narrowed down where in the subsystem it is, but it's on the right track.
But yeah, but as long as all these is running on a single box, you know it's not you have more resources available. It's essentially at that point you've proven it's a contention. It's either in a contention in the extension API server, which seems improbable given that you can get the throughput on just one, or it's a contention on the communication mechanism, but you just don't know where in that communication mechanism.
Yeah, I think if I were going to try and just confirm this, I would just make a code change and in the main API server to turn off the HTTP or disable the multiplexing, which should be possible. I don't know.
There are in fact a couple of switches already. In the I believe in there are two things that are documented. I think they're both at the Go level. One that I've experimented with is an environment variable named disable HTTP2, which completely disables HTTP2.
Yeah, it doesn't disable the aggregation mechanism. It still does it. It just uses the HTTP like 1.1 or whatever.
Right. Right. Which would be again a way of disabling the multiplexing.
Yeah. Yeah. Actually, and have you tried that? And did it change anything?
Yes, I have. It changed a lot. I got different failures. Now, my problem was that I wasn't able to get very selective. So I disabled HTTP2 basically everywhere. And that produced bad performance of a very different sort. And if you look through that document, you can see reports from experiments. In this case,
I wonder if that flag on the server actually only disables the server half of HTTP2. I don't know if it disables the client half. So it still might do HTTP2 in a client to further downstream server.
So I verified what was going on by doing LSOF on the processes and counting TCP connections. So yeah, I did that. I flailed around until I got a lot of connections to make sure that I really was disabling the multiplexing.
Excellent. And so that gave so many other problems that you couldn't really tell if it.
Yeah, it gave a completely different failure mechanism. It did not look like the direct case. It did not look like the proxy case. It was bad performance in a completely different way. And I have graphs in that document that you can look at.
So what if you disable HTTP2 on not the aggregator, but on the aggregated API server.
Well, that was my problem. I couldn't get a lot of connections unless I disabled HTTP2 on both of them.
Interesting. Okay.
Now maybe I just botched something. Maybe I'll try again. And also in the Go documentation for HTTP2, there are different environment variables that are documented. So I can try that too. So I can go back and try again, see if I can get, just the one that I want. But I'm probably going to disable it. I don't really want to disable it on the main one entirely. I could disable it on the aggregated one. Yeah, what I'd like to do is disable it on the aggregated server in its role as a server, but not as an SD client. But I don't. Well, I'll try again. I don't know if I can control that finally.
Yeah.
Yeah, this is why I think the config level, almost config level thing is I think a lot faster, and it'll get you pretty far in confirming.
Yeah, if you can make it work.
Yeah.
Yeah.
Well, but the config level thing right now, if I got this right, this is actually not quite a trivial thing, right? Because I'll need a new API of group version. So that's kind of cloning a lot of code in the sample API server.
So, well, I was going to suggest running multiple copies of the aggregated API server and putting them behind a load balancer, but I think that, or no, actually the service mechanism.
No, that'll work. That should work.
Is it still? I think it might.
No, it
still
won't.
be connection from the perspective of the aggregator.
Right, you'll still get one connection.
But the API server load balances, in fact, I think the way to do it would be not put it behind a load balancer. I'm trying to think how to do this. The easiest would be if we could convince the API server, the Kube API server, to listen on 2 ports. And then you register each port as a separate endpoint, because then what the Kube API server is going to do is load balance, and it'll start keeping 2 connections.
It goes through oh, that's right. It does figure out the endpoints and go through the endpoints. Yeah. So if you register, so if you run 2 of the backend, the aggregated API servers behind the same service, or actually, if you can run multiple of them. The aggregator should multiplex across them, and so if you run 2, you should see double the throughput.
Yeah. In fact, if you don't, let me know, because that's a bug, because I made that work.
Yeah.
Okay, well, I could try that. Right. I'll have to change the setup a little bit, because the existing sample API server has, I think it's a replication controller with one, pod template, which has both the SD server, a single standalone SD server, and the aggregated API server connected together.
Yeah, so just run one etcd, but make it 2 of the aggregated API servers.
Right, I have to reconfigure so they both connect to the same.
Yeah, but that way it's a config-only change, and you should be able to.
Right, and I can use pod affinity to put them both on the same host so that they're sharing the same CPUs.
Exactly.
And you could even once you get that condition set up. Well, I wonder. Yeah, if you could register a load balancer instead of those 2, you could figure out if it was the aggregator, but I don't think that's easy. So
yeah.
So again, let me just repeat. Let me just double check. So you're telling me that if I do get 2 aggregated API servers behind the same service, just the normal main API server is going to open connections to both and load balance the requests across those 2 connections.
Correct.
Yeah.
Okay. Well, I'll try. That sounds like the easiest thing to do. I'll try that first.
Yeah, that's a good idea.
And then it's harder, but Daniel's other suggestion, which I kind of like, is if you then put a load balancer in the way, what'll happen is so both services behind a load balancer, it looks like one endpoint to the Kube API server, and that way you'd actually confirm your theory.
Yeah, unfortunately, I don't think that's going to be easy to configure. So.
Yeah.
Right, and it doesn't totally confirm it, because then you have to ask, is the load balancer introducing a bottleneck? I think the comparison between what I've done and what we just outlined with 2 aggregated servers is a pretty direct one and a pretty good test. So I think I'll try that next.
Yeah, by the way, I really appreciate you like diving into this.
Yeah.
Yeah, this is hugely helpful.
We're stretched kind of thin, so it's super helpful to have people investigate at this level of detail. And I'm sorry I haven't been able to look at it in detail, but your document seems like a really good write-up. So appreciate that.
All right. Thank you. Yes. Well, I'm glad that I have people to work with. As I said, I think it's a good technological approach. I just want to prove it out and help make it actually good in terms of the actual implementation.
Yeah.
Thank you.
We're very happy to have the extra eyes.
Okay.
Cool.
So that's all I had for today.
All right.
And I don't think we have any agenda items, so everyone gets half an hour back. All right. Thanks, everyone.
All right. Thanks. Bye.
I'm actually confused. How